Okay. All right. So now we are getting a carry here. What do we do with the end around carry? As in this particular case, we add it with the least significant bit. So this carry we added to the least significant bit. This carry is nothing but a end around carry. So you add this, this will become 111, 111, 0110, 0011, and 0001. So what is equivalent decimal value for this BCD code? It is 136 and 7, 136.7. So you can compare here these two answers, 136.7 and 136.7. So this is how you perform the subtraction of BCD numbers using 9's complement. Maybe let us take another example where there will be no carry. Here you got a carry here, right? You got a carry here. So here you got a carry. Let us take another example where you don't get a carry. When you don't get a carry, what does it mean? It means that it is going to be a negative number and you will have to take further complement of it. That is what is the rule says. Now we are doing an example with no carry. When there is no carry, please remember that you have to take further complement of the number and you have to put a negative sign. Obviously, you can see it from the result itself, right? When you subtract 679.6 with 885.9, the result is going to be negative. Okay. Okay. So now how do you proceed? So first you have to perform using 9's complement. Hence, you take the 9's complement of 885.9. So we are going to take the 9's complement of 885.9. When you subtract it, this is 0, 4, 1 and 1, 114.0. So this is the 9's complement of 885.9. We will add these two numbers. So before that, we have to convert all these numbers to BCD numbers. Corresponding BCD number of 6 is 110, 7 is 111, 9 is 1001 and 6 is 0110. We will add these things. When you add, it is 6, it is an invalid code. Here it is 11 because 9 plus, this is 13, right? So 1011, this is an invalid code. So let us normalize this later. Let us perform the addition first. 7 plus 1 is 8 here. 6 plus 1 is 7 here. And this is an invalid code. What do? We add 6 to it. When we add 6 to it, this remains as it is. Here 1 plus 0 is 1, 1 plus 1 is 1 and 1 plus 1, here 0 with a carry 1 and then there is a carry here. This carry gets added to this particular number. That is what is being done here. And now when you add this particular carry 0110, 0011 as it is, carry added 1, it becomes 1001 and 0111. Okay. Now what is equivalent number? The equivalent number is 793.6. Please note, you are not getting any carry here. There is no carry here. When there is no carry, you have to further take the complement of this particular number, which means that what is 9's complement of 793.6? 9999.9 minus 793.6 will be 206.3 and we put a negative sign toward. So the answer is minus 206.3. This is how you perform BCD subtraction using 9's complement. So we saw two examples. One is with carry and other is without carry. Now similarly, let us perform the 10's complement also. This is also almost the procedure is very similar. Here you see this, the answer is going to be negative here. 206.4 minus 507.6. So the answer will be negative, which means that you will not have any carry. And further, whatever the added sum, after you take the complement, you will take one more complement, 10's complement of that number. So what is the 10's complement of 507.6? let us take 9's complement and add, which is the easiest way. Instead of subtracting it from 10,000.0. So this becomes 3, this becomes 2, 9 and 4. We add 1 to it. So the answer is 492.4. So this is the tens complement of 507.6. So 492.4 and 206.4 expressed in BCD. These are the BCD values. Okay, so 9 is 1001, 2. So you can write. Now you add these two things. 4 plus 4 is 8. 6 plus 2 is 8. Valid code. I'm just checking for a valid code. 0 plus 9, 9 a valid code. 2 plus 4 is 6 a valid code. So you need not perform any normalization here. So 698.8 and you are not getting any carry. When you don't get a carry, you will have to further take the tens complement of this. So what is the tens complement of 698.8? Again, you take here the tens complement is taken directly by subtracting it from 1000. But what we are going to do is we will subtract it from 999.99. So 9 minus 8 is 1, 1, 0, and then this becomes 3. So it is 301.1. You add one more to it because 9's plus 1 complement. So this is 2, 1, 0, 301.2 and you add minus to it. So the answer is minus 301.2. This is BCD subtraction using tens complement with no carry. Any doubt till this? Okay. Now let's perform with carry one. The last example maybe. Yeah. The last example. You know that this result will be a positive number. Why? Because 342.7 is greater than 108.9. We will take the tens complement of 108.9. So 108.9's tens complement is 891.1. When you add these two things, you get a carry. So you will have to ignore this particular carry in tens complement. Please recall the difference between the tens complement and nines complement. In tens complement, we ignore this carry. How do you remember? 10 is a big brother of 9. Am I right? Which means elder. So he is ignoring small things. Whereas 9's complement, you have to, this carry here is called as an end around carry and this end around carry is added here. So that is the 9's complement. Whereas in 10's complement, you ignore it. So how do you remember for what to ignore and what to keep? So this is a very simple analogy. Okay. So we will take the tens complement of 891.1 and we'll take the BCD numbers of 342.7. 89.1 is already the tens complement. So let us take the BCD of this. So 7 plus 1 is 8. So this is a valid code. This is a valid code. 2 plus 1 is 3, valid code. 4 plus 9 is 13. This is an invalid code. 3 plus 8 is 11. Again, this is an invalid code. So what do? We add 6 to it. We are adding 6 to it. We are adding 6 to it. So when you add 6, obviously you get a carry here. You add this carry to the, you carry forward this carry to the next bit. And then the final sum here is, these two gets propagated down as it is. Here it is 0011. Adding carry to 001, it becomes 0010. So the equivalent value here is, again you are getting a carry, we will ignore this carry. It is ignored carry. So the corrected difference here is 233.8. So which is similar to the already found number. Any doubt? Okay. Now we are going to move on to the XS3 code. Now again, if you go back to the table, the XS3 code is nothing but a weighted code. right? So these small questions might arise in objective type. What is an XS3 code? XS3 code is a non-weighted code. I'm sorry, I think I said weighted. It is a non-weighted code, right? And it is also a kind of a BCD code, which is also, this XS3 code is also a self-complementing code. I will define now what is a self-complementing code is, right? So now let us move on to the XS3 code. Another form of BCD code in which each decimal bit is coded into 4-bit binary is your XS3 code. As the name implies, what is this XS3? It's actually XS, but it can also be written as XS3 in short form. So each decimal, each binary bit or each coded value is added 3 to it, which means that a code is generated here. Sorry, a code is generated here by adding decimal 3 to the BCD code of the digit. Meaning, if say for example you have a decimal value of 2, then what is the BCD code of 2? It is 0010. This is your BCD code. Now what is your XS3 code is? You add 3 to it. What is 2 plus 3? 2 plus 3 is 5. So 5 is 0101. Or in other words, 0010 was the BCD code. You add 3 to it. What is equivalent of 3? It is 011 is the equivalent of 3. You added 1010. Right? So the equivalent XS3 code of decimal 2 will be 101. Okay. And certain properties of XS3 code are, they are not weighted codes because there is no weight associated with the bit positions here, and they are self-complementing codes. What do you mean by self-complementing code is, I will read this statement, definitely you will not understand. Then I will explain with an example, you will understand. That is, you take the ones complement of a code number, it will give you a nines complement of the same number itself. As promised, it did not get well with you, right? So what is this self-complementing? I'll explain it here. Say for example, I think, yeah, you take this. So this is the decimal number that we have, 395. You take XS3 of this particular number, okay? And at the same time, you take nines complement of the number. And if you take the XS3 of this, and if you take the ones complement of this XS3, both the numbers will be same. Now, still, I know that there will be little confusion. Let us take an example, then I'll show you. You take XS3 code of 395. You know that what is the code of 395? In XS3, every digit has to be added with 6. So 3 plus 3 is 6. So what is the code for 3 in XS3? It is 0110, which is decimal equivalent to 6. What is the XS3 of 9? 9 plus 3 is 12. So 1100 is the XS3 code of 9. 5 is given as 1000. How did you get 100 as an XS3 code? Because we have to add 3 to each decimal value, which is 5 plus 3. So 1100 represents the equivalent code for 5. What is given here is, we have taken the XS3 code. So we have completed this XS3 code. You take the nines complement of this 395. What is nines complement of 395? It is 406, 604. You take the XS3 of this 604. What is 6 plus 6 is 12. 6 plus 3 is 9. So the code is 1001. What is 0 plus 3? It is 0011. 4 plus 3 is 7, 0011. You take the complement of this number. Complement you know to take, right? complement every bit. 1 becomes 0, 0 0 becomes 1 1, 1 becomes 0, double 0 becomes double 1, double 1 becomes double 0, 0 becomes 1 and triple 1 becomes triple 0. Now you compare these two bits, both are same. This is called as the self-complementing codes. Again, I repeat, what did we do? You take the XS3 code of a given number, right? So maybe I'll erase the highlights so that we can repeat. You take the XS3 code of this number. Okay. Now you take 9's complement of this number and take XS3 of this number and take the 1's complement, you will reach the same number. Both the numbers will be same. Okay. So this is called as the self-complementing number. Okay. So now again I repeat, a BCD code is not a self-complementing code. What are the other codes that are self-complementing? You must remember these. The other codes that are self-complementing are 2421 is a self-complementing code. 84 minus 2 minus 1 code is a self-complementing code. Biquinary code 5043210. This code is, it might look funny, but this has been used extensively in World War II. So this code is also a self-complementing code. Now let us perform the additions and subtractions of these XS3 codes. Now when you take XS3 code, what are valid codes and what are invalid codes? That you must know. So, okay. So what are the decimal numbers we have? We have 0, 1, 2, 3. Let me write here. 4, 5, 6, 7, 8 and 9, right? Now what is the BCD code? BCD code is, or let me write the XS3 code directly here. What is 0 plus 3? 0 plus 3 is 0, 0, 1, 1. Right? So this is the XS3 code. XS3 code of 1 is 0, 1, 0, 0. Because 1 plus 3 is 4. 0, 1, 0, 1 is XS3 code of 2. 0, 1, 1, 0 is XS3 code of 3. And 0, 1, 1, 1 is XS3 code of 4. 1, 0, 0 is XS3 code of 5. 1, 0, 0, 1 is XS3 code of 6. And then 1, 0, 1, 0 for 7, 1, 0, 1, 1 for 8, and 1, 1, 0, 0 for 9. Now, what are the invalid codes? What are the codes that are left? The invalid codes now are
1 1 1 1.
Yes. Let us start from 0, right? So the invalid codes are 0, 0, 0, 0 is an invalid code. 0, 0, 0, 1 is an invalid code. 0, 0, 1, 0 is an invalid code. Okay. Now coming after this, 9, 1, 1, 0, 1 is an invalid code. 1, 1, 1, 0 is an invalid code. 1, 1, 1, 1 is an invalid code. All these are invalid codes. Now you will again see that all these, there are 6 different codes here. There are 6 different codes here. So decimal equivalently, they corresponds to 0, 1, 2, 3 and then 13, 14, 15 codes. These are invalid codes. If you get these particular codes, again we will have to follow the same procedure that we have already did. So let us perform XS3 addition now. We have to perform 37 plus 28. So now let us do the normal addition and then let us verify our answer. What is 37 plus 28? 7 plus 8 is 15, 5 remainder 1 carry and 65 is the answer. We have to get 65. So now what is the XS3 value of 37? 3 plus 6, so 0, 1, 1, 0 corresponding to 3 plus 3. 7 it is 7 plus 3. Right? So this is the 1010 is equivalent to 7. Similarly, 28 can be represented as 0101, which is 5, and 8 is 13, 1011. Now let us perform the addition. So 0 plus 1 is 1, 1 plus 1 is 0, remainder 1, and then 1 plus 0 is 1, carry 1, and then this carry gets propagated to this particular bit. So 0 plus 1 carry is 0. Look here, and then 1 plus 0 is 1, and with a carry 0, and then carry gets propagated here. It is 1, and then it is 1. Right? Now check for the valid codes or invalid codes. 0101, this is a valid code, and 1100, this is also a valid code. Okay. Now here the rule how to perform XS3, whereas in the previous case, if it is an invalid code, what you did was you added 6 here, right? But here there is a slight difference here. What is the rule here is, if you get a carry generated by the addition of these two bytes, then you will, if you get a carry, then you will add 3 to it. If you don't get a carry, you will subtract 3 to it. Meaning, here you have got a carry, right? So you must add plus 3 to it. Here you have not got any carry here. So you subtract minus 3 to it. So when you add 3 to it, this is equivalency is 5, right? 5 plus 3 is 8. So it becomes 1000. What is 1101? It is 12. 12 minus 3 is 9. So 9. So 98. Now you have to get the XS3 of this. What is the corrected SS3 of this 98? It is nothing but 65. 9 minus 3 and 8 minus 3. So 9 minus 3 is 6, 8 minus 3 is 5. So this is your corrected answer. We'll do one more example, then maybe it will be further clear. So we are going to perform this addition 247.6 and 359.4. So the equivalent XS3 code is this one. I think I need not explain this. All these are equivalent XS3 code. When you add, you are getting a carry here. You are getting a carry here. Now you perform with the carry also. You add the carry to the bits, which means that this part had carry and this particular section's addition had a carry. So, and at the same time, here when you performed the carry around here, this bit also generated a carry here. Okay. So wherever you had a carry, you have to add plus 3. You have to add plus 3. So here there was a carry, and here also there was a carry. You add plus 3 to it, and here you did not have a carry here. There is no carry. So you subtract minus 3 to it. So the answer is 0 plus 3 is 3, 7 plus 3 is 10, 0 plus 3 is 3, and 12 minus 3 is 9. Okay, so it is 607.0 is what is your final answer is. Okay, so this is how you perform. And how did I get this? I mean, I have written the answer directly here, but how did I get this is first find the equivalent value. 1001 corresponds to 9. These are decimal values, right? BCD coded decimal value I am writing. So 0011 corresponds to 3. This corresponds to 1010 corresponds to actually 10, right? Let me write 10 here, just for the sake of my convenience. Dot 3. Now these are BCD codes, but if you have a table of this particular XS3 code, you can write directly here. What is 1001 corresponds to 1001 corresponds to 6. 0011 corresponds to 0011 corresponds to 0. 1010 corresponds to 7. So we got 7 here. And 0011 corresponds to 0011. Where is it? Yeah, 0011 again 0. So it is 0. So this is your XS3 code of the sum. Any doubts? Okay. Now let us perform subtraction. Please note here, similar to this, if you had a carry, you added. If you don't carry a carry, you subtracted. Here, if you had a borrow, if there is no borrow, then you will add 3. If you have a borrow, then you will subtract -3. Right? So that is the rule. So let us perform the same thing. Here, we are not going to take any complement form. You can subtract directly. I mean, you can take complement and also you can do that. It's also fine. But this is the rule. Whenever you are getting a borrow, you have to subtract. You don't get a borrow, you add. So 267 is represented as, for 2, maybe you can have this particular table in hand. 2 corresponds to 0101, so 0101. 6 corresponds to 9 equivalent to 1001. 7 corresponds to 1010. And 1 corresponds to 40100. 7 corresponds to 1010. And 5 corresponds to 1000. You subtract 0, 1, 0 and 0. You have not got any borrow here. Here it is 1, 1. Here you are getting a borrow here, which means that this particular thing is obtained by getting borrow. Where from you are taking the borrow? You have taken borrow from here. Whereas in this subtraction, it is 0 here. 0 minus 0, 0, 0. There is no borrow that is taken in this particular byte. In this particular byte, there is no borrow. In this particular byte also, there is no borrow. Whereas there is a borrow for this. So if you take borrow, then you have to subtract -3. So -3 is subtracted here. If you don't take a borrow, add 3 to it. So 0010 corresponding is 2. 2 plus 3 is 5. It is 15. 15 minus 3 is going to be 11. Sorry, 12. This corresponds to 12. And 0 plus 3 is 3. So the answer here, what does 9 corresponds to? The XS3 value? 9 corresponds to 1100. So 1100, this corresponds to 9. And 101 corresponds to 2 here, 2 here. And 0111 corresponds to 0 here. So we have got the original answer, which is 092. Okay. Any doubt in XS3 subtraction? Okay. Now let's move further to, let us see 2 more codes. We have already said that 2421 is a self-complementing codes, and at the same time 84 minus 2 minus 1 is also a self-complementing codes. 503, 43210, they are all self-complementing codes. Now, just for the sake of an example, let us see what is a 2421 code is. Now, again, this 2421 is a weighted code. You remember that this is a weighted code. Even 84 minus 2 minus 1 is also a weighted code. When you have numbers like these, 2421, 84, they are all weighted codes. Why did I say this? Then why these numbers have come? Basic question, right? You see here, all these numbered codes, they are all weighted codes. These numbers, they are negatively weighted codes, which means that their weight is negative. Okay. Rest all bits, they are, whether it is self-complementing or whether it is reflective cyclic codes, they don't have any weights to it. A non-weighted codes, obviously, X is 3, gray, 5 bit, they're all non-weighted codes. Okay, right. So coming back to this 2421 code, yeah. How is this 2421 code is obtained? Again, as you know that these are weighted codes, 0 corresponds to 0000. 1 corresponds to the corresponding 1. Here the weight is 1, so hence it is 1 here. 2 here, now the confusion will arise whether to give priority to the first 2 or the last 2. Give priority to the last 2, which means that the 2 that is available in the least significant bit. So that is how this becomes 2. This 3, it is this 2 plus 1. 4, obviously the priority goes to the larger magnitude here, so it is 1. Now 5. 5 here, since you have used 4, 5 will have more weight than 4, right? So which means, if say for example, okay, so here there are total 9 bits, right? 9 decimal values. You can divide this into half. Okay. The thing that you must observe is why 5 is not written as 0101 is because half the bits will have 0 as your MSBs and all the remaining bits will have 1 as your MSBs. Now you must be able to find out the difference. Okay. Now at the same time, 5 will be an exact complement of 4. How? You see here that 0's complement is 1 you have here. 1's complement is 0. 0's complement is 1 and 0's complement is 1. Likewise, you take any number, say for example, there will be a complement in the opposite side. What is the complement of 0 here? It is 1111. So you see 9 will have 1111. Similarly, you take 2. What is the complement of 2? It is 1101, right? So the complement of 7 will be 1101. See, this will be a complement of this. This will be a complement of this. This I don't have place to draw. This will be a complement of this. 8 with 1 and 0 with 9. I hope this is clear. Okay. And let us come back and see the weights now. So half the lower bits now will have a larger weight. So the first one is going to be 1, right? So we are done with 2. How many? What is 5 minus 2? Remaining 3 is there. So 3 can be made with 2 plus 1. Similarly 6. So 2 priority is given to this. 4 minus 2 is 4. And then remaining 4 is given priority like this. 7, this and this. And then this 1 bit. Likewise, you create the 2421 bits. I hope I have made it clear. Okay. And obviously, there will be some bits that are unused. What are the bits that are unused here? 0, 1, 2, 3, 4. 0, 1, 0, 1 is unused. 0, 1, 1, 0 is unused. 0, 1, 1, 1 is unused. 1, 0, 0 is unused. 1, 0, 0, 1 is unused. 1, 0, 1, 0. All these are illegal codes in 2421. Right? So that is what is mentioned here, that rest are all unused conditions. Now let us come back to a negatively weighted bits. What do you mean by negatively weighted bits? So 0000 corresponds to 0. Let me erase the inks. Okay, yeah. Okay, 0 corresponds to 0000. Now I need to have 1. So its weight is given as, obviously the first bit is going to be 0. All the bits are going to be 0. So it is 4 minus 2 minus 1 is 1, right? So I give priority to my larger weight here, 1. 4 minus 2 is minus 2 minus 1 is minus 3. 4 minus 3 is 1. So these bits are 1. Similarly, 2, it is 4 minus 2 is 2. So these two bits are made 1. 4 minus 1 is 3. So 4 minus 1. And 4 is given as 1, 0, 0. And we are done with half the symbols. And the later half of the symbols will be a complement of your of the upper list of decimal values. So 5 will be a complement of 4. 6 will be a complement of 3. So what will be the complement of 0, 1, 0, 0? It will be 1, 0, 1, 1. So that is what is written for 5. Similarly, 1011 will be a complement of 0101. 1001 will be a complement of 0110. Right? So that is why it is said that these codes are actually the complementing codes. Okay, last code, this biquinary code. This particular code, why should we study this? Is because this was the code which was used in the first computer, which is not the first computer, it was used in the Colossus computer. It was normally used in World War II, and this was the world's first programmable digital computing device. So the world's first programmable digital computing device used this biquinary code. So this is a weighted code, obviously. So 0 corresponds to, you have two 0 positions here. You have two 0 positions, 0 here and 0 here. So hence it is 1 here and 1 here. 1 corresponds to there is only 1 here, and obviously all the there will always be a pattern. And how did they make these things? These are out of our scope of why did they make these like things. This is how they have programmed their system. Okay. So 0, it doesn't have weight, hence all the positions are 1 here. So 1 corresponding to 1, and then 2, 3 and 4, right? All
So,
these are ones. Yes, please go ahead.
so for 1, why can't we write the last 0 as 1?
No, they have to identify with the first half of the bits with the later half of the bits,
Okay.
right? So
Yeah.
whereas if you look at the lower half of the digits, all these, it is 5, right? So 5 is considered as the base. Less than 5, nothing is considered at the base, but still you need to represent it with a number. Hence a 0 weight has been given. You see here, it looks obviously abnormal, right? We should have 5, 4, 3, 2, 1, 0. This looks much familiar. Why was this 0 introduced here? The 0 was introduced in between 4 and 5, just to make sure that there's this might be generating some kind of a flag. And why was it not generated in front is because these two bits 5 and 0, they looked like they are signaling bits. 5 used to signal larger signals, 0 used to signal smaller signals. Though you require, in order to represent only the 9 digits, all you need is to represent only 4 bits. Okay. So, and one more thing that you observe here is, other than if you call these as signaling bits, you compare these bits, you will have only one in that particular sequence. You see in this particular sequence, there is only one here, one here, only one here. Likewise, there is only one here, and these bits are used for flagging the sign bit, or to notify the lower half of the digits. So here also you see it is 1 across the MSBs, and you will have only one along these diagonal elements, right? So this is what is the sequence that has been followed in biquinary code. Okay, right. So bi means it includes both. Bi means it is 2 states. Quinary means it is 5 states. Hence, it is called as biquinary states. Likewise, maybe you can, as an exercise, you can perform your own subtraction using 9's complement and 10's complement using XS3 code. Actually, during the physical classes, I used to give it as an assignment, but since I don't want to trouble you with multiple assignments, but these are possibilities. Okay, you can also perform the XS3 code using 9's and 10's complement, though we did not do the example there. Okay, so finally, let us look at the gray codes or reflected codes. I think these are the last part of the codes. Yeah, yes. So we have almost covered most of the things. You know what is a binary code is. Obviously, BCD we took maybe two examples: 8421 visa, 2421 visa, and the negatively weighted codes also visa. Rest all these are weighted codes you can make. We have already seen XS3 codes, right? And yeah, what is remaining is we will see now what is a gray code is, and then we will also see what is a parity codes and Hamming codes, right? Okay. Now, what is a gray code? Gray code is a code which will change, the subsequent codes will change only by 1 bit only. What do you mean by that is the advantage of these gray codes is that a number in a reflected code changes only by 1 bit as you move from one number to the next number. And where are they used is they are used in, we call it as K-map. Some of you might have studied in class 12 what is a K-map. K-map is called as a Karnaugh map, right? We will see in very detail about this Karnaugh map later. So, but currently, just presume that there is something called as K-map where these gray codes are used there. Obviously, these gray codes are not weighted codes, right? They are not weighted codes. They are used in situations where you will get errors during transmission. If you are transmitting an analog signal to from one place to another, then obviously you will transmit the bits, right? As an example, if you look, say for example, you are first sending 7, right? So you are sending 7, right? This 7 gets converted to digital, and then from transmitter to receiver, you are receiving 7. Normally, how they will get transmitted? You will not send 7, you will send it like this 0 1 1 1, and then here also you will get it as 0 1 1 1. Then what do you do is, then you will send 8. 8 is given as 1 0 0 0. Then you will get 1 0 0 0. But what happens is, please, I've already said multiple times that each bit that you are representing here, each bit here corresponds to one digital circuit. There is one separate circuit corresponding to each bit, which means that if, say, for example, due to capacitance inside that particular circuit, due to some resistance inside that particular circuit, this changing of this bit gets delayed. This 0 1 1 1 must be changed from 1 0 0 0, but this last bit is taking some time to change. Then what happens? 1 0 0 1 will be sent to your output instead of 1 0 0 1. Right? This is an error actually, right? So how do you eliminate this particular problem? In order to eliminate this problem, you must create a code such that this change takes place, or the change here takes place only by 1 bit. For example, yeah, it is already mentioned here. This problem is eliminated by gray codes. Only 1 bit will change between two consecutive numbers. This is very important. So for a normal 2-bit binary number, what do we do? You see here, there are 2 bits. 0 is changed to 1. Fine, no issues. But moving from 1 to 2, here 0 is also getting changed to 1 and 1 is also getting changed to 0. So 2 bits are changing. And last, 1 is as it is, 0 is changing to 1. Whereas in case of gray codes, your first code, if it is 0 0, only 1 bit will change. That is, this particular bit has changed now. 0 has changed to 1. Then what will happen is It will not change to 1 0 as in our conventional binary bits. The 0 gets changed to 1. Then in next sequence 1 will change to 0. So only one bit changes at any particular point of time, and these kind of codes, they are called as gray codes. And these gray codes, we don't use it for any arithmetic operation. Okay, right. So any doubts so far? Okay, so I think we will stop here because next we will have to cover little bit of concentration is required. So we will stop here and then let us see in the next class. Any doubts so far? If you have doubts, please let me know.